Okay, so this video is going to cover problems 61 through 70. This will be 61 through 70, and beginning with problem 61. Last year, it was calculated that recreation expenditures were 8.7% of total personal consumption, and economists believe that the percentage is going to go up as we move further out of the recession. Consider a hypothesis test of P equals 0.07, in other words, 8.7%. Versus greater than that. Which of the following choices of significance, a level, and sample size results in the greatest power of the test? So we were looking to increase power. Well, what increases power? Once again, power goes up if alpha goes up. Power goes up as the sample size goes up. Power goes up as beta goes down. So as type 1 error goes up, power goes up. As the sample size increases, power goes up. As beta goes down, type 2 error goes down, power goes up. So we're going to be looking for, since we want power, the greatest power, we're going to be looking for the greatest alpha, the greatest sample size, and the greatest type 2. They had nothing with type 2, so we're going to be looking at alpha. Well, 0.10 is larger than 0.05, so this is gone. So these have exactly the same alpha, so I need the largest sample size. The largest sample size is this, so the answer to number 61 is D. All right, number 62. In comparison of the life expectancies of two models of washing machines, the average years before breakdown in a simple random sample of 10 machines of one model, which is compared with that of 15 machines of the second model. The 95% confidence interval estimate of the difference is 6 to 12. All right. Which of the following is the most reasonable conclusion? Well, first off, we never ever talk about probability. We never ever talk about, we never talk about probability. So let's look at these. The mean life expectancy of one model is twice the year of the other. We didn't say that. We just said the difference is between 6 and 12 years. The mean life expectancy of one model is 6 years, while the mean life expectancy of the other is 12. We definitely didn't say that. We just say that the difference is somewhere between 6 and 12 years. We don't know if it's as low as 6 or as high as 12, but somewhere between there. We didn't say how long either one of them last. The probability, we never talk about probability when we talk about confidence intervals. Again, the probability, we don't ever talk about probability about confidence intervals. We only relate, so we're down to only one. We should be 95% confident that the difference lies between 6 and 12. That's basically saying, that is basically our conclusion statement. We are 95% confident that the true population difference in life expectancy lies within the interval 6 and 12 years. So basically, this is essentially a restatement of our confidence interval definition. All right. Oh, I'm sorry, I'm on the wrong problem. We should be moving on to problem number 65, which is absolutely a tricky question. So number 65, on a windless day, a member of a high school football team is punting specialist kicks, says toe, this should say two identical footballs, one filled with helium and one filled with air, 10 times each. He alternates footballs and is not told there is any difference. The distance in yards of the kicks are recorded in the table below. Assuming that all assumptions for inferences are made, which tests should be used to determine if there is a statistical difference in yards kicked using the two balls? Well, for me, this is going to boil down to real quickly, is this going to be a two sample or paired? And then, of course, we have the Z versus the T. So let's address Z versus T first. They did not give me the standard deviation of the population. So that means I'm going to have to get the standard deviation from these values, which would be the standard deviation of the sample. So that gets rid of anything that has to do with the z-test, because I know I'm having to use the standard deviation of the sample. So now I'm left with two sample versus paired. So the first thing is, are they the same length? The answer is yes. So that means it could be either one. If they are not the same length, it can't be a pair. So once again, and we've not talked about linear regression in a long time, so you can just assume that for the time being it's not. With this would be a predictive model, and we're not looking at doing a predictive. We want to do a probability. Is there a difference? So my question is, do we have a natural pairing? And if so, what was tested twice? Well, tested twice. Oh, this could be the kicker. Well, that would be kicker one. And this kicker would also be kicker one. It's like, wait a second. We don't have multiple kickers. So had this been multiple kickers, this could have been done as a paired, because the kicker would have been, each kicker would have been tested twice. Since we only have one kicker, we have the average distance for kicker one and the average distance for kicker two. So this becomes a two sample t-test. I would need to have been tested. If I would have had 10 different kickers, each one kicking one helium, one air, then I'd be controlling for differences between the kickers. I'm not controlling for differences between the kickers because I have only one kicker. I'd need multiple kickers. I don't have that. Okay, number 66. To test whether husbands or wives have a greater manual agility, a simple random sample of 50 married couples is chosen, and all 100 people are given a 1-minute period to find and place strangely shaped pegs into matching holes. What is the conclusion at a 5% significant level if a two-sample hypothesis test results in a p-value of 0.15? So we're running a two-sample hypothesis test, and we have mu1 and mu2. So we're running, this is not running as a paired. Let's pause for just a moment. Okay, so they set this up as a two-sample hypothesis test. So the observed differences between husbands and wives is significant. Well, that's a pretty large p-value, so that does not appear to be that significant. So don't really like that answer. The observation is not significant. Well, that's not quite true. They didn't give us an alpha level, so we but well, at a 5%, so it's not significant at the 5%. So this is a possible answer because that's true. The observed difference is not significant at the 5%. A conclusion is not possible without knowing the mean number of pegs. That's not necessary. Conclusion is not possible without the mean standard deviation of the number of pegs. Not necessary. A two-sample test should not be used. Is this best run as a two-sample test or a paired? And the answer is we have 50 married couples. So if we have 50 married couples, we have a natural coupling, we should always run a paired when possible. In this case, it's possible because it would be possible to compare a married man to a married woman, or a married woman to a married man. You can measure the couples because we already said that we have them. So consequently, while this is a plausible answer, it's not the best answer. And letter E is the best answer because we can actually run a paired test. All right, we have the ability to run a paired test. All right, number 67. Administrators working for a national sports association randomly picked 20 Division I and 30 Division III football programs and ran a two-sample inference to compare the mean GPA of football players in the two divisions. All right. A p-value of less than 0.05 resulted. Which of the following is a proper conclusion? All right. A p-value of 0.05 is pretty small. And typically speaking, if they don't give us an alpha level, we use alpha 0.05. If they don't give us one, if they don't, and since they didn't here, we would be rejecting the null that they're equal. All right. So it cannot be concluded. Well, no, it could be concluded. It cannot be concluded. No, it could be concluded. It cannot be concluded the observed difference in mean GPAs is significant. Were randomly selected. Guess what? Randomly picked. It cannot be concluded that observed differences in mean GPAs is significant because division programs were excluded from there. They weren't testing division 2. They're only testing division 1 and 3. It can be concluded that the observed differences is significant, right? It can be concluded that the observed differences is significant. All right. So the question on this is, how do I know to use a two sample? Well, basically, obviously, I have two independent groups. And if you have two independent groups, you're stuck with a two sample. And then you go, well, is it really? Well, is there a natural pairing? Well, you don't have, it would be fairly difficult to do a pairing with this. I can give you an example where it'd be possible to do a pairing, but I could compare one team's quarterback to a Division I quarterback to a Division III quarterback. But they would have to tell me that they had matched positions so that I would have a testing of twice. Since they didn't, I have the average of, I have two independent averages for Division I and averages for Division III. So that makes that a two sample test. A high school has 6 math teachers and 6 science teachers. This is number 68. When comparing their mean years of experience, which of the following is most appropriate? Okay, I have 6 math teachers and 6 science teachers, and I'm comparing their average years of experience. If I know all the math teachers and I only have 6 here, and I have 6 science teachers, I'm not taking a sample, I'm taking a census. And because I'm taking a census, no test is appropriate. All right, no test is appropriate when I'm taking a census. Now, I could have used a 2 sample t-test. I could have used the 2 sample t-test if I said I took a sample of 6 math teachers and a sample of 6 science teachers, because then I'd be saying I didn't take the entire population. Here it says I took the entire population. So obviously, since I'm not taking a sample, I've done a census. This is going to be none of the above appropriate. So if I had a sample of 6 math teachers, I randomly selected 6 math teachers, I randomly selected 6 science teachers, I compared, and I found the mean difference from my sample and used that to estimate my population, then a 2 sample T would be appropriate. As far as when I could use the 2 sample Z, I would have to have known the standard deviation of the population. They would have had to tell me that in the problem. The standard deviation of the population is this. If I calculated it from the sample data, then that makes it a t-test. And since I have 2 independent groups, it would be a 2 sample T. So realistically, this could have been either done as a 2 sample T, or since they did a census, it's going to be none of the above. Question 69. 2 pain relief medicines are tested on random samples post-operative patients at the 5% significant level as whether or not mean durations of relief are different. The data given below. All right, first off, it says, what is the conclusion of a 2 sample t-test? Well, I need to go ahead and run this thing. So give me a moment. I'm going to pause this thing while I input the data because I haven't done that. Okay, so resuming the recording, it says, what's the conclusion? Well, so I input this data into my 2 sample T, and it looks something like this. That's 2 sample T number, which is number 4. So stat test number 4. And X bar of 131, standard deviation of 12, sample of 20. Did the same thing for B. Now, they said different clues me in that I need to be using a not equal. We never pool for means. And I ended up getting a p-value of 0.067. So our p-value is greater than 0.05. So we're going to fail to reject the null. Now, one thing I did not see up here, these are small sample sizes. So they should have told me that the population was normal. I needed to know the distribution was normal. They didn't say that, so I probably shouldn't have run this test, but there was nothing that indicated that. If there had been something that said, hey, we shouldn't run the test because we don't know the underlying population, that would have been the case. So how did I know to run a two sample? There's a couple reasons. First off, my sample size, I can't run a paired if my sample sizes are different. To run a pair, I'm going to have the sample size that are the same size. So that's one clue. Also, just thinking about this, is a paired possible? So to be, in this case, we have a post-operative pain relief. So it's not really realistic for me to sit there and go, well, we gave him this medication, then we redid the surgery and gave him a different medication. So I couldn't very easily test it twice. And I say that carefully because technically I could sit there and go, I randomly selected which one each patient got. And so this patient got this one first. And so we gave it to him. We gave him brand A first. And then after it ran out, then we went and did brand B and vice versa. So it's possible that you could have waited until the pain came back and re-administered. But really speaking, probably not something you could have tested twice. And if you can't test it twice, or there's not a natural coupling, it can't be paired. Okay. All right, number 70. A college recruiter is interested in comparing the SAT, math, and verbal scores of applicants to the college. A simple random sample of 40 applicants is chosen and the math and verbal scores are noted. Which of the following is a proper test? Well, so in this case, we can be looking at one of two things. We're looking at two different things, a math score and a verbal score. So we're going to be either looking at a two sample or a paired. Well, I know that I have 40 applicants and I have their math and their verbal score. So essentially they were tested twice. And since they were tested twice, this is going to make this a paired test. So one sample test on the difference of paired data. Now, could this have been run as a two sample? And the answer is yes, it could have been run as a two sample. I could have randomly selected 40 math scores and then randomly selected a group of 40 other verbal scores and compared the average verbal and the average math, in which case, if I'm comparing two separate groups, it would be two sample. But in this case, we have a simple random sample of 40, so we only have one sample. And from that one sample, I took two readings. So I basically tested them once on their math and once on their verbal, so that makes that paired data.